Okay, welcome back, all the participants. Now we will have two more lectures in this session. Each one will have 30 minutes time. Yeah, 30 minutes time. Let me call the first speaker of the session, Professor Thangaraju Dheivasigamani from PSG Institute of Technology and Applied Research, Coimbatore, Tamil Nadu, India. Professor Thangaraju Dheivasigamani will speak on the topic high temperature wet chemical synthesis of two-dimensional chalcogenide nanosheets for photodetector applications. Professor Thangaraju.
Good afternoon, all of you. Thank you very much for the introduction. My name is Thangaraju, working as Assistant Professor, Department of Physics at PSG Institute of Technology and Applied Research. Today I am going to present our piece of our work about high temperature wet chemical synthesis of two-dimensional chalcogenide nanosheets for photodetector applications. In this particular work, I'm going to present one beautiful part of our work. So this work, so we have done this work along with the collaborators available. Our collaborators available in Aviro, University of Aviro. I also in our PhD Institute of Technology, I have established nano-crystal design and application laboratory with the help of fund got from the Department of Science and Technology, Government of India. So with this facility, we have grown a very various kinds of nanomaterials from microstructures to nanostructures and quantum dots also. So outline of today's work is first I will introduce two-dimensional nanostructures, particularly on layered metal dichalcogenide semiconductors. And then I am going to give the peculiar idea about the synthesis method of tin disulfide using different solvent combination. Particularly, we have used different high temperature boiling point solvents. So I have used different solvent combinations so that I am going to give those combinations and its outputs. And after that, the characterization, in that particular topic, we are giving peculiar idea about materials and its formation while it is grown with the different solvent combinations. Okay, and then we have fabricated photodiodes with fabricated photodiodes with the synthesized tin disulfide nanosheets. So that I am going to show, and its characterization also. Finally, I will conclude this topic. So when we talk about two-dimensional materials, suddenly we got the idea about graphene, mostly the first two-dimensional material that the scientific community know. So because it has worked, it harvested a vast attention about among researchers, because it shows great promise for wide range of applications from optoelectronics, catalytics, and many other applications. So after graphene, if you think about two-dimensional nanostructures, suddenly people talk about two-dimensional metal dichalcogenides with the combination of transition metals, fourth group elements, along with the sixth group sulfur, selenium, telluride. So it has wide, it represents a big family of compounds. Mostly it forms AB2 type structures. So A represents molybdenum, tin, niobium, gallium, tungsten, along with the sulfur, selenium, telluride. And here we are more particularly interested on tin and sulfur combination. So because the ultra thinness and two-dimensional morphology and also single or phyloid thickness is possible with these kind of nanostructures. So ultra thickness and two-dimensional morphology mostly enable in this material with ultra high specific surface area compared to their bulk materials. Okay. So because of its two-dimensional structure, it shows high flexibility, good mechanical strength due to unique two-dimensional features among this material. Yeah. So most of the people explored the various promising applications in electronics, optoelectronics, sensors, and even in biomedicine also. The people working on this particular material. So this particular material gets application in battery, solar energy conversion, supercapacitor, and hydrogen generation. We are concentrating particularly on sensor applications, particularly photosensors. Okay. Our interest material is tin disulfide because tin disulfide is outstanding two-dimensional N-type semiconducting material. It shows applications in optoelectronics from solar cell to detectors, even in hydrogen generation applications. So, in particularly tin disulfide shows a lot of stoichiometric ratios: tin sulfide, tin disulfide, tin 3 sulfur 4 combination, tin 2 sulfur 3 combinations. Okay, we are interested in particularly tin disulfide because it is N-type semiconducting material for our application purpose. We can grow two-dimensional material using this particular material. So even in tin disulfide, we have many polytype structures. Tin disulfide shows 2H, 4H, and 6HA, 6HB polytypes in tin disulfide. So for two-dimensional material, particularly concentrate on 2H because very simple layer by layer structure is possible with this particular polytype. So this it shows hexagonal. So layer by layer structure is possible. So here the picture shows the metal atoms are architecturally coordinated to the chalcogenide atom and form a triple SNS layer structure. So 2H shows SNS only. So 4H, 6H shows SNS, SNS, SNS like expansion. For simple layer by layer structure is possible with the 2H, so that our point of interest is towards tin disulfide for this particular investigation. So most of the synthesis method for tin disulfide are generally two-dimensional materials, mostly prepared using explosion method, CVD, chemical vapor deposition, and then solvothermal method. So these methods are complicated because explosion leads a lot of defects in its surface. CVD is very costly, and then the hydrosolvothermal we can't able to predict, and the reproducibility is very less in this particular area. So that we wanted to try different synthesis method. So because if you see the phase diagram, in solid state, it is very difficult to maintain tin disulfide alone. So here you have the combinations with the solid state. It is very difficult because tin will be dominated in particular combinations, sulfur will be dominated in a particular combination of sulfur. So so solid state, the explosions mostly based on crystals. From crystals only you can exploit single layer. To maintain a single phase, we wanted to choose a particular synthesis method and to control the sulfur and tin segregation. So and also we can avoid tin trisulfide, tin disulfide, tin to trisulfide, these kind of excess combinations. So that I wanted to choose a synthesis method that is precursor hot injection method. So in this method, we do the precursors were dissolved in high temperature boiling point solvents like oleolamine, oleic acid, and octadecene. The boiling point of this kind of solvents are more nearly 310 around. So we choose all the three solvents for this investigation. First, we start with oleolamine. Oleolamine is taken in two different flasks, flask A, flask B. The precursors such as tin 2 chloride and sulfur were used as precursors. So tin in both flasks, we take tin in A, flask A, sulfur in flask B, dissolved in oleolamine. So it was degassed at 100 degrees centigrade, because we in our synthesis method, the oxygen is against our system. If oxygen is there, automatically tin oxide will form. So we wanted to get a single phase tin disulfide, so that in order to avoid those unwanted situation, we degassed this system. So after getting clear solution, the solution B that is available in flask B is loaded in syringe that is injected into the flask A at 250 degrees centigrade. So after clear solution available in tin chloride that is heated up to 250 degrees centigrade, the solution is ready. After that, the flask B solution is injected. So at 250 degrees centigrade, the material is formed. This is the idea what we have used to synthesize tin disulfide. In this, we have chosen different solvent combination. The first S0, SN, S2 is synthesized with only oleamine. So S0 represents oleamine. The both flasks were filled with oleamine. And this S1, S2, so S1, SN, S2 is synthesized using the combination of oleamine, oleic acid, and octadecene. So we have chosen less amount of oleamine and oleic acid in the large amount of octadecene to check the output. Okay, so the third one we have chosen S2, SN, S2. In this, only oleamine and oleic acids to check the morphology change. So octadecene in this sample is avoided. So hereafter I will mention S0 for oleamine, S1 for oleamine, oleic acid, octadecene, and S2 for oleamine and oleic acid. So for after synthesizing this material, the materials were washed with acetone and then dispersed in hexane, cyclohexane. So after synthesis, first we wanted to know the structure of the material, and also with the XRD we can predict the nature of the material. So we have done XRD for all the three different material that is synthesized using different solvent combinations. So first S0, SN, S2 is taken for measurement, and we found two different structures such as SNS and SNS2. So because here in this material, SNS belongs to P-type semiconductor and the SNS2 is N-type semiconductor. So mixed formation is arised. So that was confirmed with JCPDS data that is given in this figure. So S1, SNS2 and S2, SNS2 is somewhat pure, but both were free of SNS mixing. So these two curves, the green curve and orange curve shows purity of the material. So both is well matched with the tin disulfide JCPDS data. So with this, the sample that is synthesized only with oleolamine is not good. So because oleolamine is very vigorous, so that it leads the sulfur. Once tin disulfide is formed, it try to dissolve, and the sulfur and the tin will be grown and regrown type is happen inside the oleolamine, so that the SNS formation is more in this second more. So the octadecene introduction in this synthesis controls the dissolution of SNS2, so that the XRD results comes from the both oleic acid, octadecene, oleic acid introduction in the synthesis controls the SNS that we have confirmed with this XRD. Okay. So next, very interesting study is Raman. With this Raman, we have confirmed the nature of the material, whether it is single phase or it is flatness of the surface or multi-phase. Okay? So we have found intense observed peaks were fitted with the 2 strong Raman active modes. So mostly thin disulfide were predicted with the 224 and 312 centimeter inverse. So that was observed all those 3 samples. Okay, so all those 3 samples, the base material of all those 3 samples is SNS2, so that it is confirmed first. And then we found that generally 166, 224, and 312 centimeter inverse, which is assigned to B3. 3G of SNS2 and the EG and the A1G of SNS2. So B3G mode that is observed for S0 SNS2 that is at 166. That the intensity of this peak is very, very small. So the combination of SNS and SNS2, the SNS2 may be in large amount. So SNS may be very little amount. In XRD also we have confirmed. So in this, if you change the solvents, like mixing of 3 solvents, mixing of 2 solvents, shows there is a missing of peak at 224. So here in a S1, SNS2 shows 2 peaks, 224 and 306. It seems the peaks, the shape of the material is 3-dimensional in nature. So that we got 2 different modes in SNS2. In S2 SNS2, the last sample, that shows only 1 peak, which shows the flatness of the surface. Flatness surface may be possible, so that can be observed in a SEM analysis. With this Raman, we can conclude that S2 SNS2 shows only 1 peak, so that it predicts that the synthesized material is 2-dimensional. Okay. In S1 SNS2 sample, we can observe two modes of EG and A1G modes. So with this, the sample is somewhat 3-dimensional. Okay. So and also there is a shift in S1 SNS2. Usually the A1G mode of SNS2 arise at 312 centimeter inverse to 314 centimeter inverse. But in our case, S1 SNS2 shows there is a shift in lower centimeter inverse. So there is a reduction of scattering. In-plane scattering is evidence for ultra-thin nature of the sample. That is primary thing. And the material may be the shift may be due to the strain of samples. So in our TEM analysis, we have seen orbicular structures that is formed inside the material, so that the strain may be confirmed with this Raman analysis that represent in red color. So before analyzing the microstructure of synthesized material using TEM, we wanted to see the shape of the material with the scanning electron microscopy. So here are the results that informed from A, B, C pictures are the material synthesized using polylamine only, and S2, the materials are two different morphologies. One is layer morphology, and along with the layer there is a disturbance. So small amount of disturbance is there. Maybe that is arised from tin sulfide mixing. Okay. So the second material, that is S1 SNS2, that is synthesized using octodecene polylamine oleic acid combination. Here we can see the uneven edges of the material. The material edge is not even. So and also the thickness of the material by looking this SEM, it is look like a disk throw. So this was confirmed with the TEM analysis, and with these pictures there is two-dimensional sheets, but there is no proper edge. There is no proper edge with surfaces not even. So and the S2 shows somewhat hexagonal shape particles. The edges are very regular. The edges are defined. Okay, so with this, we got a little idea about our synthesized particle. So we wanted to take TEM to know more information about our synthesized material. So first we got TEM results of SNS2 material that is synthesized using only polyamine. Here you can see two kind of particles. One is unshaped contorted structure along with secondary particle. So as I mentioned in the XRD, I gave an idea about dissolution of tin disulfide. The dissolution is continuing for long time, even it is stored in cyclohexane. So after storing it in cyclohexane, the sulfur and tin disulfide is dissoluting, and along with that, the tin disulfide is formed. The formation of two different structures are confirmed with the HRTEM image. So 120 plane belongs to SNS structure, and if 101 plane is the predominant plane of SNS2. Okay, so in the shade pattern also we have confused dots that is appeared, so we can't able to predict whether it is arised from SNS2 or SNS1. Okay, so after doing this, we wanted to know the SEM image of tin disulfide synthesized using three different solvent combination. Here, the secondary particle is completely controlled. As we have seen in the SEM, the edges of this particle is not defined. So it is look like a lotus leaf, and based on the orbicular structure that is appeared in this particular area, the arrow mark area, it is looking like a disc throw sporty equipment. So maybe the center portion of this material, the leaf structure is having higher thickness than the edges. The edges were not defined. So as like the thing. Once if you introduce oleic acid and octadecene, the growth of tin disulfide is completely controlled, and also the structure is somewhat definable. So in previous case, we can't able to define the structure, and once it is oleic acid is introduced, we got a controlled structure. Here, the really beautiful HR10 image shows the 100 plane of SNS2. So with the shade patterns, we got very beautiful spots. That spots with that spot you can define the planes. That is the X-ray spots that is viewed from the top. So next, once if you with only polyamine, we got mixed structure. With the addition of oleic acid and octadecene, we got the leaf-like structure, that is lotus leaf-like structure, and we got an idea to remove the octadecene to check the output. So only polyamine and oleic acid combination shows the beautiful hexagonal structure with the controlled surface. So in previous case, you can able to see the orbicular nature of the particle. So with this, we can conclude the disc shape material. Here, you can almost the transparent area of this material shows there is a uniform surface. So uniform surface with Raman S2 SNS2 sample shows only one peak. So that was there we have predicted the material is flat in nature. Here that was confirmed. So I accidentally we got a chance to take the side view of this material. So we have measured the plane, that is 001 plane, which means the 100 plane is extended along 011 plane. We got very flatty nature of the material. So in this case of S0, S1, S1, S2, we don't get any side view of material, but in the case of S2, SNS2, we got side view. It composed of 12 atomic layers, so we can able to see the layers that is composed to form a single layer. The outside of this material is due to surfactant. So if you consider only within the structure, we got a beautiful layer by layer structure. We counted that we 12 layers that form the one thick one disk. That is not a disk; it is a flat two-dimensional SNS2 sheet, nano sheet. Okay. So after getting these three materials, we wanted to know the photoresponse of this material, because the S0 material is synthesized with only single solvent that leads two different material SNS and SNS2, and the second two materials are purely different morphology. One is leaf-like morphology, and one is hexagonal flat, and the leaf-like with the disc shape. So, for that purpose, we use we wanted to construct a photodiode with silicon substrate, P-type silicon substrate, because SNS2 is dominated with N-type. So N SNS2 and P is silicon. So with this synthesized material, we fabricate photodiode. Okay. So for this, we have followed a certain coating procedure. So first we choose silicon substrate. Silicon substrate mostly have native oxide layers. To remove native oxide layers, prana solution and HF solution combinations were used. After cleaning this, we have coated this synthesized material, because after synthesizing tin disulfide, we have stored those materials with cyclohexane. So we directly use these tin disulfide that is dispersed in cyclohexane. So we have followed the same kind of coating for all the three materials. We have maintained same ratio between cyclohexane and the particle. So we have found a layer. The heat treatment was done under vacuum. So we use vacuum for a vacuum furnace for heat treatment. So after that, the silver is used as a to create a foamy contact between SNS2 and the silicon substrate. Yes, after fabricating, we have measured IV characteristics of three different solvent combinations synthesized in tin disulfide. So all the materials have tin disulfide particles, because only one material, that is S0, SNS2, only the mixing of P-type and N-type. So automatically it disturbs the function of this diode, the first S0, SNS. After these two, that is the tin disulfide material that is synthesized with three different solvent and two different solvents. So for three different solvent leads the disc shape, and two different solvent leads flat hexagonal shape. So the first diode, we know the output is not that much good. So we expect some difference between these two structures. So once if the material is created and the IV characterization is checked, the SN, S2, SNS2 and the S1, SNS2 shows the beautiful difference that is observed in IV characterization. So with IV characterization, we have calculated the ideality factor, barrier height, and reverse saturation current, and photosensitivity, responsivity, some photosensitivity parameters, quantum efficiency, and specific detectivity. So as we have predicted before, as NS0 based photodiode shows a very low, very high identity factor, that is 12.56 and 13.808. So that is normal because the SNS particle is mixed. There is a huge electronic dispute between SNS and SNS2. But we got a difference between the structure. So S1, SNS2 shows very poor in ideality factor, and SNS2 shows very good ideality factor when not compared to ideal diode. So ideal diode, the ideality factor of ideal diode is equal to 1. But these two results, that is calculated for S1, SNS2 and S2, SNS2 shows huge difference between these two. So with this, we can predict the layer formation with disc-shaped particle shows a huge difference than the flat particles, flat sheets. So my prediction is if the flat sheets are combined together and they can form easy transportation of electron, if you form this disk shape, there is a discontinuity between one layer to another layer. So because here we are, the layer is synthesized and then it is formed as a thin film. So the seating of flat layer is easy, so that tin disulfide flat layers shows ideality factor closer to ideal diode. So and also we have compared the photosensitivity. Photosensitivity shows very high for flat layered tin disulfide, that is S2, SNS2 based diode. This also, because in first sample we have mixing, so photosensitivity obviously less. So when you go for different structure, the photosensitivity of both S1, SNS2 and S2, SNS2 is somewhat the same, but the difference that is created with the flat layer is high. So that based on the photosensitivity parameter that is calculated using IV characteristics, confirmed that the flat layers may easily transport electron between one layer to another layer. So with this, I conclude our results. Tin disulfide nanostructures were synthesized using 3 different high boiling point solvent combinations using oleamin, oleic acid, octadecene, and hexadic patterns reveals that the sample synthesized using mixed solvent results single phase. So both mixed solvents were using all the three, and oleamin with oleic acid shows single phase. Only oleamin leads multi-phase. So multi-phase can be controlled using oleic acid and octadecene. So SEM and TEM micrographs reveals the orbicular structure and hexagonal shape nanostructure for S1, SNS2 and S2, SNS2. So we can differ using SEM and TEM analysis. The photodiode was successfully fabricated using a synthesized SNS2 nanosheets on P-type SI substrate. The ideality factor value of fabricated N-type S2, SNS2 on P-type silicon photodiode somewhat closer to ideal diode. So our idea is not discussing the things, particularly SNS material should be synthesized in a single phase. That is, since it is having more polytype material, we wanted to control the polytype and then get a good output among the single phase. So with this, I thank organizers for giving me opportunity to present our little beautiful result. And I also thank our collaborator, that is Thangarajan, M.A. Valenti and M.P. Grasa from I3N Avido, Department of Physics, University of Avido. They also participate in this particular research. And also I thank Chandrasekhar and Nadu for providing me opportunity to do photodiode characterization in their laboratory. And also finally I thank Igor for giving me this opportunity to present my my work. Well, thank you.
Okay. Thank you very much, Dr. Thangaraju. Thank you for the nice presentation.